And hence, this is the first example of hyperkahler. Now, the point is that there are many Lagrangian fibrations on such type of manifold. So maybe I will speak a bit more about Kessler surfaces in the first example. Okay, so I'll raise this general picture, but you will see it in some other lectures.
Could you switch to black marker, please?
Sorry?
Black marker, could you switch to black marker?
Black marker is better. Ah, okay.
Yeah.
It's fine. It's not visible. Or?
Yeah, not much.
Ah,
It's shiny.
okay. So I raised this definition. This definition was for general Lagrangian fibration. And what I'm going to do. Okay, so Kessler surface, so the kind one of the advantages maybe of complex geometry is that they are moderate. That means if you have a complex structure, there are variations. So topologically, it's difficult to vary usual manifold, real manifold. You make small variation, this kind of remains topologically the same. And that's, but if you have a complex manifold, it's topologically remain the same, but as a complex structure, a structure of function in many different ways, there is variation. And then you can, what is good sometimes to degenerate, but you won't do it. So now we have, so let's say S4. So the surfaces, so Kessler surfaces of degree 4 in the screen. So the number of parameters of non-isomorphic surfaces is the number, so the number of parameters is 9. So there is a space, so that what does it mean? It's a so-called dimension of the modular space. So this is dimension, what is called modular space, dimension. Modular space. Of degree, again, degree 4. Degree 4. It is simple to compute because what we have is, so this is basically the difference. So this is the difference of the number, the space, dimension of the space of 4 of homogeneous polynomials of degree 4. So take all homogeneous polynomials of degree 4 of 4 variables. Minus, and then under the rotations of projective group, we have to make equivalence on the rotation on the action of the projective group, which is the minus dimension pj 3, pj 4, which is which is okay. So the total space. So we compute one space minus another, and that's the dimension. That's a variation. This is the space which parameterizes non-isomorphic, but non-isomorphic with the same degree. That means we can same embedding, modular embedding of Kester surfaces. Now, the point is, among them, there is an 18-dimensional subset, everywhere dense, subset of surfaces which have Lagrangian fibration. So first, this is an example. This is what is called hyperkahler manifold. And among those hyperkahler manifolds, there is an everywhere dense subset, parameterized actually by union of what is called devices, so algebraic varieties of dimension 18, which have Lagrangian fibrations. So it is quite often. So that indicates the fact that they appear quite often, and they are much easier to analyze than the general Kester surface. So in here already, in this case, we can see one of the phenomena of the hyperkahler movable. First, by a very small variation. So if you have basically, if you have a polynomial of degree 4, there is an epsilon variation of coefficients such that the resulting variety will have a Lagrangian fibration. In that case, Lagrangian fibration is what is called elliptic fibration. So in this case, we have S4 Lagrangian fibration over P1. So the base of the projection, and here we have ET, but it is a generic fiber. So the map is cannot be everywhere smooth. So therefore, we have. You see, it's easy to see because so if you look at S4, then H2 of S4 is equal to 20 to 22, 1. So we have numbers, whole numbers 1 to 1, 20 to 1. So therefore, Euler characteristic is 24. But Euler characteristic of elliptic curve is 0. So if all fibers would be elliptic curves, then they will have a contradiction simply with Euler characteristic, this simple formula for it. So in case, generically, so for generic S4, we have 24 singular fibers, and these singular fibers I draw like that, yes, but that means you have P1, so projective line with one point of self-intersection. So it's like smooth projective line, but one self-intersection point, and this is the singular point of the map. So therefore, in this case, certainly we have a one-dimensional fibration. Form is dimension 2, so nothing to check. Means every smooth, every one-dimensional subspace of C2 is always isotropic. So therefore, it is Lagrangian automatically. Lagrangian fibration over P1 and 24 fibers like this. That's a picture of generic, what is generic elliptic fibration. So I want at the moment to describe all aspects, so on this, all practical aspects of the theory, can be seen on the level of case surfaces. And I explained why. So the other aspect is that case surfaces